Yes.
Perfect. Yes, I'll talk about verification of co-simulation algorithm here, which has been something that we have been looking into the last couple of weeks. So first of all, I'll just declare what a co-simulation algorithm is, just so everybody is on the same page. So basically, in order to obtain trustworthy co-simulation result, we need a correct master algorithm. Like the master algorithm, that's the one dictating what the different simulation units should do during a simulation. So therefore, we really need such a correct master algorithm. So just to give you sort of a feel of what such a master algorithm looks like, it's like an ordered sequence of the function calls which we like execute on the simulation units during the simulation. So I have just presented a small example here of two FMUs which are being connected, and the master algorithm contains both the initialization procedure and the stepping function. And just for this sample example here, the stepping function would be that first you would get the value here, then you would set it here, and then you would, and the order of these function call is like important, and basically the order is the topological order of the graph you obtain by creating a dependency graph between these. So what makes co-simulation or master algorithms difficult? So basically, each co-simulation scenario is different. So there needs to be a unique configuration of the master algorithm for each unique co-simulation scenario. And when we're talking about scenarios, we basically divide them into two different types, like the trivial scenarios and the non-trivial scenarios. I will show you some example of these later. But also, it's not only the scenario, but also the implementation of each of the FMUs affects the configuration of the master algorithm. And that's you if an simulation unit is using interpolation or extrapolation. And then, of course, it's also the function of the order of the procedures is also important. So basically, you could ask yourself, how do we ensure correctness of such an algorithm? And the answer is, not surprisingly, we built a formal tool that we can use to like verify a master algorithm. So the whole idea is that a user here, he has this co-simulation scenario. He develops the master algorithm, and then he feeds both the scenario and the master algorithm into the verifier, and then we basically tell him if the master algorithm is correct with respect to the scenario or if it's incorrect. And if it's incorrect, then we would basically like to show the user your master algorithm is incorrect, and here is the reason why. But when we are left with the question, but how do we actually build such a tool? So first of all, as we talked about, like different co-simulation scenarios, like requires different configuration of our master algorithm. And when we're talking about scenarios, we have these trivial scenarios where we're having no algebraic loop. Like an algebraic loop basically means that a port of the simulation unit or an FMU port depends on itself. And trivial scenarios, they can also, it's scenarios where like a fixed step co-simulation algorithm can be used. So basically, if this is the case, when like rollback is not a part of our co-simulation algorithm. But on the other hand, we also have like non-trivial co-simulation scenarios where we either have like algebraic loops or the scenario cannot be simulated using a fixed step co-simulation algorithm. And I've just shown you an example of these. But also, as we talked about earlier, the implementation of the FMUs themselves also affect the configuration of the master algorithm. And the implementation of the co-simulation or the FMUs. So when we talked about extrapolation and interpolation, we just basically mean how do an FMU calculate its future state. So if it's extrapolating its state, it's using inputs from the current time to like extrapolate here its future state. And when we have like compared to like interpolation, where it actually knows the future value and it's using that to calculate the future state. And basically what this means, it has an effect on the configuration of the master algorithm, because in order for an FMU to achieve its value from a future time point, that affects the stepping order of an FMU. So basically, when we know all of this, we can like put up some criteria for what a sound master algorithm is. So basically, as we saw, the order of the function calls in the master algorithm, it should be correct. And it means obviously that a value should be retrieved from one FMU before we could set it on another FMU. And when we talked about these interpolation and extrapolation, and it's referring to the input types of an FMU. So the delayed input port means an FMU is using extrapolation, and reactive means that it's using interpolation. And also a correct master algorithm should also ensure that we have some kind of time progression. Otherwise, the co-simulation will run forever. And when we are talking about algebraic loops, we should perform some kind of stabilization. Otherwise, we will not obtain a deterministic co-simulation. And also, after performing all the steps in a single co-simulation step, all the FMUs should be at the same time. So basically, we could just say, okay, a sound master algorithm should satisfy all these criteria that we have here. Unfortunately, that turns out to be a bit naive, since then we will not be able to handle non-trivial co-simulations example. And I have an example of that. So if we're looking at a non-trivial co-simulation example, here you can see we have 4 FMUs, where 2 of them are like involved in an algebraic loop here, you see. And we have 2 FMUs over here that cannot be a part of a fixed step co-simulation algorithm due to that FMU C and D might reject to perform a given do step. So in this non-trivial example, as we stated earlier, then we need to have like a rollback in this. So if you remember the constraints I talked about earlier, so we have these constraints and the setting and getting of these input ports, and whenever 2 FMUs, so right now we are trying to find a common step between these 2 guys, but in case we are not succeeding in this, so the 2 FMUs will have a different time step, then we will break some of the constraints or some of the contracts that we defined earlier on a master algorithm. And it turns out that this violation is unavoidable, but rolling back our FMU to like a former or a previous state can give us an extra chance to find a common step. And basically, we could do that until we find such a common step. But that leads us to, in order to solve this scenario, we need to reformulate our original formulation of what a sound master algorithm is. So for trivial scenarios, we can like reformulate it so it will never break one of the contracts that we defined earlier, and eventually the master algorithm will terminate, so it will not run forever. But for like non-trivial scenarios, so a sound master algorithm will, for non-trivial scenarios, eventually find a configuration that does not break the FMU contracts, and it will eventually terminate. So it just means, for this example, at some point we will succeed finding a common step for these, and then we will be able to like satisfy all the contracts that we stated earlier. So we have implemented this in UPAL, the model checker UPAL, as 4 templates, and the implementation is based on the FMI standard and based on the definition of like a sound master algorithm that we just defined. And you can just see here, so we have basically the 4 templates is an interpreter that takes a master algorithm and a scenario and performs the step or performs the operations of the master algorithm by invoking them on the FMUs. When we have a step finder for solving like finding a common step between the FMUs in case this is required. We have a loop solver for solving algebraic loops for stabilizing these. And we have like the FMU from the FMI standard, which are basically encapsulating all these constraints that we talked about earlier. And it's also like having the symbolic state of the FMU. Just to know, there's each of these inside a simulation, but there will typically be multiple FMUs. So the interpreter, I'll just talk briefly about 3 of these. So that's the main entity of the verifier, and it pretty much takes the role as the master algorithm, and it performs all the steps from the instantiation of the FMUs to the termination. And basically, I have just shown you how the simulation works. So it has multiple states. So it will come in here into the simulation mode, and then it would simply look at to see, okay, should I invoke an action on the FMU, and then when that is performed, it'll go back here. Or should I find a common step between one of the FMUs? So it's basically invoking the other templates and ensuring time progression, and eventually it will terminate if there is a correct co-simulation algorithm that is being supplied. Otherwise, it will end up in a deadlock, which will be presented to the user. So, and here we also have the FMU template. So the FMU template defines the type of FMU you have, like the number of output ports, the number of input port, and their type. So if it's a delayed or reactive input. And also, it also defines all the states an FMU could be in based on the FMI standards. So it could be in the initialization mode, it could be inside the simulation mode, and so on. And it also captures all these contracts that we defined earlier. So every time you try to invoke an action on an FMU, it would basically check the precondition, or it would check the contract as a precondition on the scenario. So it will check that you are not setting a value that doesn't conform to the contracts that we stated earlier. And of course, you cannot set a value on an input if the FMU is unloaded. So it will just verify all these constraints. And then basically we have these 2 other templates, the step finder and the loop solver. And the point with those is just that both of these they violate some of the contracts that we stated earlier. So these templates, they need to find a configuration of the master algorithm that will not violate the contracts. So when we are looking at the step finder, we need to find a common step of all the FMUs, because we know that such a step will not violate the contracts that we stated. So the step finder repeatedly performs a procedure of actions until we find such a common step. And so basically inside the step finder, we disable all our contracts because we know it will violate them. And then once we have identified a correct step to take among all the FMUs, we will turn the contracts on again, and then we'll run an extra iteration of the co-simulation with these configurations, and then we would verify that all the contracts are being satisfied here. Yes, just to sum up, we developed a formal model in UPAL for verifying co-simulation algorithm, and we have been able to show time progression and verifying the procedure for solving and stabilizing algebraic loops, and for verifying the procedure for finding a common step size, and essentially we verified the order of the function calls. Yeah, so if we should look into the future, what we currently are doing is creating a tool to generate these scenarios. Claudio, the next speaker, he's taking the lead on this work, and then we still need to do some testing of this approach and to trying to see, okay, which type of co-simulation scenarios cannot be tested by this. And then we would also like to implement new FMI features such as flux, which are new FMI free standard. And we would also like to see if right now, if a co-simulation master algorithm is not allowed, then we would just get a deadlock, but we would try to see if we can present the mistake in the algorithm to the user in an intuitive way. Yeah, and also as Casper, he talked about earlier, we would like to see how we can integrate this work into the Maestro 2. Yes, thank you for your time. Bye.
Thanks so much, Simon.